I love seltzer water, right? You put carbon dioxide under pressure, you increase the solubility of the water, right, in terms of how much carbon dioxide it can hold, and you make carbonated water, right, more carbon dioxide dissolved. So what's the point besides the fizz? Well, first of all, right, this doesn't follow Henry's law exactly because carbon dioxide reacts with the water. Carbon dioxide reacts with the water to make carbonic acid. So again, why do I like seltzer water? It's because of the carbonic acid. That's what gives a little bit of a taste to the carbonated water. So what kind of a reaction is this? Is it a precipitation reaction? No. Is it an acid-base reaction? Well, no, not really. There's not really something donating an H and something accepting an H. I mean, H's are there, but I don't see an H donor and an H acceptor. Is it a redox reaction? Well, when I go through systematically and look at the change in oxidation state, no, it's not a redox reaction either. So what is this? Well, this reaction fits into this category called a Lewis acid-base reaction, where I have something that's an electron pair donor and I have something that's an electron pair acceptor. If you remember from bonding before, in order to form a bond between two atoms, this one donates an electron to the bond, this one donates an electron to the bond, and we get a bond. Well, in this situation, both of the electrons are coming from one species, right? Both the electrons are coming from the water to make the bond between the water and the carbon to get this intermediate. This intermediate then falls apart, right, by having this electron pair being donated. So this hydrogen gets transferred over to this side of the molecule, and they end up with carbonic acid. So an acid is an electron pair acceptor in the definition of a Lewis acid-base reaction, right? So H plus donor with Bronsted, electron pair acceptor if you're being an acid with the Lewis definition. And the base is an electron pair donor. Here we have a nice picture of a orbital with an electron pair in it and an orbital with no electrons in it. So both of the electrons are being donated. Well, I should say it this way, right? You're going to get an overlap, right? This is how we visualize bonding occurring. And both of the electrons are coming from the X, right? So from X orbital. So in this case, X orbital is acting like the Lewis base, and the empty orbital is acting like the Lewis acid. So for example, boron trifluoride breaks the octet rule, right? You've got 3 fluorines bonded to that central boron. This electron pair gets donated by the nitrogen in ammonia, and you end up forming a bond between the nitrogen and the boron. So both of the electrons are coming from the nitrogen. This is the classic example of a Lewis acid-base reaction. Again, no H is being transferred here, right? It's electron pair donation coming from the Lewis base to the Lewis acid. So identify the Lewis acid base amongst the reactants in the following reactions. All right, so a classic with Lewis acid base chemistry is complex ion formation. So if we get rid of the spectator ion here, what is the spectator here? Well, I guess we don't have potassium chloride, so there isn't a spectator. So what I have is the waters complexing with the iron 3. So 6 waters, each donating an electron pair, covalently bond to iron. So all of a sudden, hey, weird stuff, right? Iron forming covalent bonds? Yeah, that's what happens when you complex. This is where you get color changes, right? Why is cobalt 2 in water pink? Why is copper 2 in water blue? Why is iron in water kind of this orangey red? Well, when you get complexes, a lot of times you get a color. So when you get something, highly oxidized like iron 3, I mean, iron is a pretty unreactive metal, right? I managed to take 1, 2, 3 electrons away from it to get a +3 charge. This thing's hungry for electrons. Now, it's not strong enough to remove the electrons from the water, so this is why you're stuck with a sharing situation. So these electron pairs get donated to form covalent bonds with this iron 3 to help lower the potential energy of the system. So water is acting as the Lewis base here, right? The electron pair donor, and the highly charged cation is acting as the Lewis acid. All right, now I didn't want to confuse these guys. I always look at this as a Bronsted acid-base reaction, but in this topic, technically, right, since the cyanide is acting as an electron pair donor, it's acting like the Lewis base. So cyanide donates an electron pair, and the H gets transferred. So an electron pair donor, right? The H being transferred. I don't know. I'd rather look at this as a Bronsted acid-base reaction. This one's more the classic, right? So the electron pair is being donated by the nitrogen. It's acting like the Lewis base. The electron pair acceptor is the boron. So again, sp2 hybridization with the boron. The electron pair gets donated. And you end up with sp3 hybridization now around the boron by having the electron pair being donated by the nitrogen. So Lewis acid-base chemistry. So again, right, I'd rather look at this in Bronsted acid-base chemistry, right? H pluses being donated. So the H gets donated. I'm sorry, the electron pair gets donated by the NH group, NH2 anion, so it's acting like the Lewis base, and the hydroiodic acid's acting like the Lewis acid. So the one we want to focus on is complex ion formation. This is going to have a lot to do with this next topic, where we get into solubility changes with different insoluble solids. So these are very spontaneous reactions. So when you talk about complex ion formation, right, there's the metal ion acting like the Lewis acid, and then there's something acting like the Lewis base, which they call a ligand. So the question is, how many ligands get attached to that that metal cation? That's called a coordination number. So there's a predictability here in terms of how many ligands you get attached to the metal cation in the complex ion formation. So these are very spontaneous reactions. They're very large K values. Kf stands for the equilibrium constant you get in the formation of a complex ion. So 2 ligands would be with the silver plus ion. So if you have a +1 charge, you can make a prediction that you would get 2 of those Lewis bases to attach. If you've got a +2 charge, you could get 4 ligands to attach. So 4 cyanides covalently bond with the copper. The cyanides are acting like the Lewis base. And cobalt-3, you could get 6 ligands attaching, right? 6 ammonias. So again, look at those K values, really big. So these are very spontaneous reactions.